a function with two inputs and one output, since the number of inputs and outputs together is 3, that could be visualized by looking at the graph, right? We've got, in three-dimensional space, we have enough to show the inputs with the outputs. A function like this, we could think of the two inputs as giving your location in the xy plane, and then the one output we could think of as giving you an altitude. So if for every location in the xy plane we have an altitude, then we're going to create the surface, maybe like some part of the surface of the Earth, or the surface that creates a mountain. Let's look at an example. Maybe f of xy equals x squared plus y squared. In other words, the output z is equal to x squared plus y squared. Now we recognize that as one of our quadric surfaces, right? An elliptic paraboloid that's opening up. Or maybe another example, maybe g of xy is equal to x squared minus y squared. So z, our altitude, is a function of our position in the xy plane. Z is x squared minus y squared. We recognize that because if you set x equal to 0, you have a parabola that opens down, right? And then if you set y equals 0, you have a parabola that opens up. Really, for every fixed y location, you have a parabola that opens up. So we see that we are getting a hyperbolic paraboloid, hyperbolic paraboloid. Hyperbolic paraboloid in this case, just to remind you. Because if we freeze z, like we freeze z at say 1, we're going to see a hyperbola. But if we freeze with x equals 0, we see a parabola. If we freeze with y equals 0, we see a parabola. So it's mostly parabolas, hence the name paraboloid. The other direction is hyperbolic, so as opposed to an elliptic paraboloid is the other possible case over here. In this case, if you freeze z, you see ellipses, hence this guy is an elliptic paraboloid. Okay, so the point is, anytime you have a function with two inputs and one output, then its graph is a surface. So when you see that kind of function, you know that you can visualize that. You can look at the graph, and the graph is going to be some surface. Let's see. We could give an equation, an example of a linear type of surface here. Maybe we have 2x minus 3y, right? So z is equal to 2x minus 3y. If we get the z alone, or if we get 0 on one side, so we get the variables all over on the other side, 2x minus 3y minus 1z. So this is the equation of a plane, right? The normal to this plane is given by the coefficients of x, y, and z, 2, negative 3, negative 1. So that surface, our normal comes out 2, goes back 3, and goes down 1. So back 2, out 3, down 1. This is our normal, so the plane we're talking about is through the origin and perpendicular to that given normal, to the normal that we read off from the equation. Notice that if it's linear, it can be written as a matrix. Since there's one output, the matrix has one entry. And since there's two inputs, the matrix has two entries, 2 and negative 3, and that's getting multiplied by a matrix of inputs, this vector x, y. So the linear ones always have a representation that is as a matrix. Another way, so if you look at this function, since there's enough in R3, we have enough space to depict two inputs and one output, we know the graph of this is a surface. But we could also do something else. If you have a surface, just imagine maybe some hill here. So can't see that on the back side, but we've got a function here that has two inputs, x and y, and then for each location in the xy plane, then we have an altitude z, and so we have a surface. But we could actually use just 2 dimensions to depict this surface. What we could do is we could just look at all of the inputs that have the same value for the output. Yeah. So think about all of the inputs in the xy plane where the output has the same value. So I'm going to slice this surface with a plane of constant z. It's going to hit that surface, right? Now we could just look down in the xy plane at that curve of values that all have that same altitude. So we call this a level set, or in this case, since we're cutting a surface with a plane, then this is one of the level curves of this set. So maybe this is the level curve that goes with z equals 2. So I could label it over here with z equals 2 so people would know what's going on. If I go up to z equals 3, then I get another different level set, right? These are all the values that have the same, cutting the surface with z equals 3, these are all the values that have that same value of z. If we just look at that curve in the xy plane, we see this curve, right? So if we just look at it in the xy plane, this is the level set that corresponds to z equals 3. If we go down and look at the level set that corresponds to z equals 1, we're going to get another level curve. And so, which if we look in just using 2 dimensions to depict that, we can just show this level curve and label it z equals 1 so that people know. So we have 3 dimensions. The graph is a surface, we can look at the surface, but we could also just look at the level curves. If you've ever looked at a topographic map, then this is familiar to you. The level curves are the lines, are the contours, the lines of constant altitude. So we have, think of this in terms, thinking of a surface in terms of its contours. The advantage here is that even though it's 3-dimensional, I can depict that 3-dimensional thing just using 2 dimensions, and that's why it's used for maps, right? A map is a flat sheet, but we can depict all the points that have the same altitude, and you can get a sense from those points what the shape looks like. So a second representation then would be to look at the level curves.